Here's one of the tutorial questions that you've been working on. It's an I-beam, or an H-beam if you prefer, that is fabricated out of 10mm thick steel plates. So you'll see all the plates are 10mm thick. There's that one, this one's 10mm, that one's 10mm. This one is 60mm wide, and so is this one. This one over here would be 100 minus 10 minus 10, which would be 80mm from there to there. And all of them are assembled together by welds, which we're going to not include in the calculation. And remember that this is a cross section through a beam which has a certain length. We're not told what the length is yet, but that's immaterial because we are interested in this particular cross section shown hatched like this. Okay, so we've got to find the second moment of area of the section about an axis passing horizontally, that's this way, through the centroid. Now the centroid, without even working it out, we know is going to be right at the middle of the form of the whole shape because it is symmetrical up and down. So the centroid is going to be over there. So we're going to have to find the second moment of area about an axis passing through that point, and then later we're going to find the radius of gyration as well. So first things first, we need to break up the shape into known shapes, and quite clearly there are three rectangles, and I've chosen to break it up into that rectangle, this one here, and another one at the bottom. 1, 2, and 3. So there are the areas of each of those rectangles, and then we've summed it to get a total area. Normally at this point we would then use the areas to find the position of the centroid, but as I said earlier, the centroid of this symmetrical shape will indeed be at the midpoint over here. So we're not going to need the areas for that purpose, but we are going to need the areas later on, as you'll see when we use parallel axis theorem. Okay, so starting with shape 1 or area 1, it's this rectangle over here, which has its own centroid at its middle point over there. Okay, which using some arithmetic would turn out to be 45mm from the final axis where we want everything about. So if you take the 100, halve it, you get 50 from here to here, and you subtract that little 5mm over there, and you're left with 45mm. We're going to need that in a moment, so take note of that. Next step is to consider area 1, which is this rectangle as discussed, and determine its second moment of area about an axis passing horizontally through its own centroid. Now its own centroid is going to be denoted with lowercase g's like that. And remember, for a rectangular shape it is BD cubed over 12. Breadth times depth cubed over 12. Easy way to remember it is B is this way in line with the axis that you're dealing with, and D, the one that gets cubed, is perpendicular to the axis that you're dealing with. So B is 0.06, remember we work in base SI units, so that's meters, 60mm expressed as meters. 0.01 is the 10mm expressed as meters, it's the one that gets cubed over 12, and there's your answer, 5 times 10 to the minus 9 meters to the fourth. Next step is to take that answer of second moment of area about the shape's own centroid and now convert it to the distant axis where you actually want the answer. So you want the second moment of area about this axis, which is some 45mm away from where you have it currently. For that, you're going to use the parallel axis theorem. So there's the 5 times 10 to the minus 9, the original answer, plus, remember, A times distance squared. A being area, so this is where we use that area, and it goes over there. And the 0.045 is the distance between the original axis and the new axis where you desire the answer. And there you'll see the new value, 1.22 times 10 to the minus 6 now, meters to the fourth. That is the second moment of area of shape 1, not about its own axis, but about this axis here, 45mm away. Right, then we move on to number 2, which interestingly enough is easier than number 1 because its own center of gravity or centroid coincides with where you want the answer. So you're simply going to say I2GG is the same as I2 capital GG because it's already there. So once again, B, which is this way, remember, parallel to the axis, which is the 10 millimeters converted to meters, times 0.08, that's this one, perpendicular to the axis in question, 80 millimeters converted to meters, 0.08, it's the one that gets cubed, remember, over 12, and there you have the answer. So now GG total for everything is going to be one of those for this one, and again the same number, in other words that number multiplied by 2, because exactly what happened on this side is going to happen for this one here, which we haven't dealt with yet, but because of the symmetry, I3 and I1 will have the same effect, so that's why we have a times 2 here. So the 1.22 10 to the minus 6 was multiplied by 2 because there's 2 flanges to this I-beam, plus 426, that's this one here, which needs no parallel axis theorem because it's already about an axis passing through the centroid where you want the final answer. So you can add it all up. 2 of those plus 1 of those gives you that answer. And that is I, second moment of area, of the whole shape about an axis passing through here. 2.8666 times 10 to the minus 6 meters to the fourth. Now to find the radius of gyration, remember that k is root I over a. So there is your I value, and there is your total cross-sectional area value. So 37.9 millimeters is the distance from the axis to this imaginary point where we could pretend all the area to be concentrated. Remember, go back to the definition of radius of gyration to better understand that. Okay, there was another way of doing this which may or may not be easier or simpler, and that was to consider a full rectangle minus 2 side rectangles, a completely different approach. But basically what it means is you pretend that we have a big rectangular shape that is solid, and we work out its I value, and then we subtract from it one of those and one of those. The only advantage to doing it this way is there's no parallel axis to worry about, because all of those would have had their centroid, or the axis passing through their centroids, all exactly where you want it. So here's how you would do it. BD cubed over 12, which would be B times D cubed, this distance cubed over 12, minus 2 of these. Remember, these are the bits that are now subtracted, which would be B times D cubed over 12, B times D cubed over 12. 2 of them, there's the 2, and you end up with the same number as before. So that would have been an alternative approach. And just to confirm, using CAD as we've done before, if you look at I about YY, which is the red axis, it is the same number you've just come up with. Now, taking it a step further and assuming that that cross section was in fact a section through a beam, as per this example, which is simply supported at its left end, its right end, and loaded at its midpoint as per the question, you would find that the bending moment would peak here at the midpoint. It would be 0 at the ends, and it would increase until it reached a maximum at B. And the bending moment at B would be either the left-hand side or the right-hand side, whichever way you decided to work. In my case, I've taken, really doesn't matter because of the symmetry, 0.5 W being either L or R. So let's for now assume that we covered up this side of the beam and just left this side exposed. The bending moment at this cross section where our hand is placed would be R, which is 0.5 W, multiplied by 2.5 meters. So the bending moment at B would be 1.25 times whatever W was. And remember that the stress in the outermost fiber, sigma, is my over I, that very important bending formula which we discussed a little while ago. And we are told that the stress may not exceed 250 megapascals. So let's make the stress 250 megapascals. Insert bending moment at 1.25 W. Multiplied by Y. Remember what Y is? It is the distance from the neutral axis here to the outermost fiber, which is 0.05. Let's just check where that came from. Let's go right back here. 0.05 would be 50 millimeters. From the axis to the outermost fiber is 50 millimeters, whether you go up or whether you go down. Remember, the stress is 0 here, and it increases until it reaches a maximum in the outermost fibers. So that is where we design for. So that is the distance, 0.05 meters. And then finally, below the line, we have I, which we now know is 2.866 times 10 to the minus 6. And we solve for W. You can have no more than 11.466 kilonewtons acting at the midpoint of this particular I-beam if you are not to exceed 250 megapascals in the outermost fibers. This is extremely useful to you in your design career from here onwards. In this next one, we have a composite beam that has been constructed out of 3 different steel sections. First of all, why would you do something like that? Well, had you just had the rectangular hollow tube, it might not have been strong enough for the job in question. So had you placed it on 2 supports here and loaded it somewhere, you might have found that permanent deformation occurred. So you could then strengthen the beam so that it better resisted bending by adding material on each side. Okay, and in this case the material was added asymmetrically, which is going to complicate matters a little bit. But the point is, if you were to take a cross section through the beam at any one point, such as this section with a view XX, you would see what you see over here. There's the original rectangular hollow section, and welded to each side is a full 6 meter length. In other words, right from the one end of the beam to the other end of the beam is this piece added underneath and this piece added above, which, as you can imagine, would significantly strengthen the beam for bending about this horizontal axis. Okay, now the first step is to find the centroid, because we can't just say it's in the middle, because we have more material on the lower side than the top side. So the centroid will not be at the center of the total height. It will actually be a little bit lower, because as you can see, this is where most material was added. So let's do that. First of all, break it up into known shapes. So I have shape 1 and shape 2 and shape 3. Zooming in a bit, there is shape 1, which is a rectangle. There is shape 3, which is a rectangle. No problem with either of those. Shape 2, however, is a rectangle within a rectangle. Now you may recall we did this using the total area, and we subtracted from it the missing area inside, and that's what happens over here. Okay, so having said that, let's look at the various areas. Area 1 is easy, 0.05 by 0.006, 50 millimeters, 6 millimeters. There is your cross-sectional area of this piece over here. Number 3, let's do that next. 0.05, it's that distance, by 0.02, which is this distance. The drawing is slightly misleading. This is in fact full width. You'll see the 50 millimeters is the same as the actual rectangular section, so I could have drawn this over here, but it doesn't make any difference. The fact is it's 0.05 by 0.02, which is 1,000 times 10 to the minus 6 square meters, this cross-sectional area here. Okay, let's go back to 2. 0.1 by 0.05 would be this by this. 0.1 being 100 millimeters converted to meters, and the 0.05 being the distance across. And then subtracting from it the missing bit inside, which would be 0.096. Let's see where that came from. 100 minus this wall leaves you with 96 millimeters. Okay, so that is the distance from here to here, 96 millimeters. Multiplied by the distance from here to here, which is 46 millimeters, which you obtain by saying 50 minus this piece leaves you with 46 millimeters. So there is the total area of this bit here, which is the hollow rectangular section, cross section. All of that area is that much. So the total cross-sectional area of the entire composite beam is that. Now, to find the centroid of all of this, you take the total area multiplied by bar y. Now, bar y is the distance from your reference edge, which I'm going to make the bottom over here, to wherever the centroid is. And I've used that symbol to indicate centroid. So bar y is the distance from your reference edge to this centroid that you're looking for. That's bar y. So area total times bar y is equal to each individual area multiplied by its distance from the reference edge to its centroid. So let's have a look why we've got 0.123 for number 1. Where's number 1? That's this one up here. How far is it from the reference edge to its own centroid? Well, it's 123 millimeters right to that point, and you obtain that by arithmetic. Just go and have a look at the dimensions. 20 plus 100 is 120, plus another 6 is 126. But remember, that's taking you right to the top. Subtract 3 millimeters to get to the centroid, which would leave you with 123 millimeters. There it is there. Right, next one, number 2. How far is it from its centroid? Number 2 centroid is at its midpoint. From the midpoint of area 2 down to the reference edge is 70 millimeters. 20 plus half of 100, which is 50, and there you have the distance for number 2. Number 3, on the other hand, is probably the easiest to understand. Half of 20 is simply 10 millimeters from number 3's centroid to the reference edge. There it is there. So bar y is 46.59 millimeters from the reference edge to the centroid of the whole composite shape is 46.59 millimeters. So before we carry on, let's decide where are the fibers, the outermost fibers that are furthest from the centroid. Okay, now it's 46.59 millimeters from the reference edge to the centroid. And it is more than 46.59 from the centroid to these fibers here. So in your final calculation, just remember that this is going to be the distance that you are most interested in. That is going to be the one that you use with the bending formula, because these fibers are the ones that are living the furthest from the centroid. These are closer, so they're not going to be the problem. These fibers here are going to see the maximum tensile or compressive stress when this beam is bent or loaded such that it is bent about this axis, which will also be called the neutral axis, by the way, the axis where there's no stress. So down to business. Second moment of area of shape 1 about its own centroid. Remember, BD cubed over 12, B D cubed over 12 gives you that value, 900 times 10 to the minus 12. It's not the axis where we want the answer. We've got to use parallel axis theorem and find the distance from here to this new centroid that we have down here. And that turns out to be 76.41 millimeters. On your neatly labeled large sketch, I need you to go in and find that 76.41 millimeters and make sure you agree. So here we go with parallel axis theorem. Original answer, 910 to the minus 12 plus area times distance squared between original axis and desired axis. And there is your answer for I1's second moment of area about an axis passing through the centroid of the whole shape. On to number 2. Okay, its own second moment of area is full rectangle, BD cubed over 12, minus missing rectangle. So it's the full rectangle, the outer, as though everything was solid inside, minus the bit that is not there. Here it is here. Check your sizes. We've discussed them already with the areas, the 50 millimeters and then the 46 by 96 for the missing piece. We've done that already over here. And you get an answer. But now, unfortunately, that's not the axis where you want it. You've got to find how far it is from 2's own axis to the actual axis where you want it. And once again, using arithmetic, make sure you agree with 23.41 millimeters, which is the dimension you're going to use in parallel axis theorem. Original answer plus area times distance squared between original axis and new desired axis. So there's your new answer. And the last one, number 3, in exactly the same way, I3 about its own centroid, BD cubed over 12, there it is there, BD cubed over 12, plus area times distance squared. That distance being the distance from the 3's own centroid to the new desired axis. Again, 36.59 millimeters on your sketch. Make sure you agree with that distance. And there's the answer. Now we can add all of these underlined numbers together because they are all about the same axis, GG. Capital GG denoting an axis passing horizontally through the centroid of the whole shape. You may add those 3 together because they are about a common axis. And there's your answer, 4.2195 times 10 to the minus 6 meters to the 4th. Okay, lots of pitfalls, places where you can make mistakes, mostly with dimensions. So the key to this problem, and I've said this before, is the fact that you have a large, clearly dimensioned sketch with no ambiguity, so that you can read off it and get all these important dimensions that you need. Right, so now we go back to the bending formula, sigma equals my over I. Remember how it works. Stress in the outermost fiber is bending moment times distance from neutral axis to outermost fiber. And we did discuss that a little while ago, that the furthest distance to an outermost fiber was going upwards from the centroid. So 79.41 millimeters is that distance. Where does 79.41 come from? Well, there's the centroid. It is 76.41 to the centroid of 1, but remember there's another 3 millimeters to get to those outermost fibers, the ones that are going to feel the maximum stress. So 76.41 plus the 3 gives you 79.41 millimeters. So that is what you're going to use as a value for y. It is the distance from the axis through the neutral axis to the outermost fiber. It doesn't help you go downwards because that's a lesser number. You want to see the furthest distance from the axis to any fiber that is the furthest away. It turns out to be 79.41. Okay, below the line is the I value for the whole thing, and you are solving for M. How much bending moment can the beam experience without exceeding 240 megapascals? Turns out that it's that much. And if we go back and look at what value of W would cause such a bending moment, W over 2 exists here and it does exist there. W over 2 multiplied by 3 meters, because remember the max bending moment is going to occur at the middle. So W over 2, which is a support reaction, and once again you can either use the left hand side or the right hand side of the beam. Let's use the left hand side for now. The right hand side is covered up, my hand is over here, and I say right, the bending moment is half of W, which is the value here, the magnitude of L, and you multiply it by the 3 meters and you would get the bending moment. Now the bending moment may not exceed 12.75, so we solve for the value of W that would cause such a bending moment, and it turns out to be 8,500 newtons, which would mean that if you were to load a mass of 866.46 kilograms at the midpoint of this beam here, you would achieve, in the outermost fiber, which is the top fibers, you would achieve 240 megapascals of stress. And if you're loading it downwards, it would be a compressive stress.